eventually, so what are the management and monitoring capabilities that are provided by Kubernetes community and Apache Ignite community if you eventually could succeed with the deployment in that environment? And usually I try to show some demo during my talks, and today I'm going to show how to deploy Ignite with persistence in Microsoft Azure. So let's go on and start with database specificities. So when we talk about a database, distributed database, it's a collection of nodes of our cluster, right? And if to turn this into the terms of Kubernetes, we need to deploy a collection of pods that represent our distributed database. And basically, Kubernetes, as we know, assigns IP addresses at runtime when you start your application, when you start your pod, which brings some challenges for distributed databases, because they need to know, like, all those nodes of our distributed storage have to find each other somehow, and by default they don't know IP addresses of each other. So we want to see first, that's actually something that has to be solved by a database engineer. But second, after that, once we found out how the database can be deployed there, how each node will discover each other, we as application developers need to decide where our applications will be deployed, inside of Kubernetes or outside of Kubernetes. Because depending on our choice, the connectivity between your capabilities and the connectivity between your database within Kubernetes and your applications might vary. And finally, it also depends on whether you go stateful or stateless deployment. Stateful deployments in Kubernetes, as we know, allow us to enable persistence. But as for the stateless, we still can use in-memory databases or caches, etc., but the data will be lost during restarts. Okay, so let's look into their discovery of nodes, and that's actually what's usually provided by a database project vendor. So technically, the input is the following. So each node of our database doesn't know an IP address of the other. And how do we share IP addresses of all the nodes that are started in Kubernetes? Turns out to be that we can leverage from one simple service that is available in Kubernetes. As it's shown in this picture, we can deploy a Kubernetes service, that's just standard Kubernetes service, and we can instruct it to look after all the pods that are started in this environment with some specific name, with some specific label. For instance, if you're going to deploy Ignite, then every Ignite pod will be labeled, let's say, as Ignite. And the service that will be started in the same environment will be instructed, to look after all the pods that have name Ignite in their configuration. And what this gives us in return? It gives us an ability to connect to this service and ask for all the IP addresses of the other pods with the same name that are available in Kubernetes. And this eventually allows us to assemble our distributed cluster in that environment. If we take a look at this flow diagram, imagine that we already have some Ignite cluster deployed in Kubernetes, and now we are booting up additional node there. This node doesn't know anything about this cluster. And first thing to do, it connects to this service that is deployed here. And the service returns all the IP addresses of the nodes that are already up and running. And after that, our new node takes one of the IP addresses and initiates that join process. And after that, it becomes a part of the same cluster. And actually, that's one of the probably most straightforward ways how you can support auto-discovery of your databases in Kubernetes. From the configuration level, this service literally looks like this way. So we are just creating simple service configuration, and the only one thing that is different, from other configurations is that you need to say that the application name or pod's name should contain this label. And that's it. After that, this service will be collecting and keeping addresses of the other pods that are available there. And now Ignite node will connect to this service. When it joins the cluster, gets all the IP addresses, and becomes a full member of our distributed database. And there is a special component in Ignite and other databases that actually deals with this connectivity, with the booting of our nodes. In Ignite, we call it an IP finder. And actually, this IP finder is like in Ignite is a pretty simple thing. You just go into Ignite configuration, you enable this IP finder, and you're saying that you are going, so like every node has this configuration, and we are telling the node that you need to connect to the service deployed in Kubernetes that have this name. So the name can be different, but it's assumed that in our case, that will be the service name. And when the node boots up, it connects to the Kubernetes service using that simple API, and that's it. This is actually how what a database vendor or needs to do, to support deployment of the database in Kubernetes. That's like the basic step, and you're good to go. For us in Ignite community, actually took just one day, like once Kubernetes, like several years ago, when Kubernetes became an extremely popular solution for provisioning, we just decided to sit down and implement this IP finder within a day, tested it out, and release it in one of our versions. But at that time, this supported Ignite was used as memory, as a distributed cache, or as a memory database. And by default, initially, we provided a memory option for deployment in Kubernetes. And so right now, let's see what we need to do if we plan to deploy, let's say, an in-memory database. Ignite, Redis, let's say, NoSQL, MongoDB. I guess those databases also support deployments in Kubernetes. So if to talk about Ignite, right, so Ignite, this actually table describes all the memory configuration options that are used for production environments. The first one is a memory option. The second one is Ignite is used as a distributed cache or data grid on top of your existing deployment, where, let's say, Oracle database, Postgres database, or MongoDB database are used as your system of records. And the last two options are used when you utilize Ignite persistence as your distributed persistence layer that is a part of your memory architecture. So now we are going to look into the first row, how to deploy Ignite as a memory layer, and then at the end I'm going to demonstrate you how to deploy Ignite with its persistence enabled, so that we keep all the data on disk in addition to RAM. So speaking about in memory, it's really straightforward. All you need to do is just, you don't need to use any stateful sets and all those advanced configurations in Kubernetes. You can utilize that simple Kubernetes deployment entity. And this configuration, actually, what it does, we just need to provide some name for our cluster pods, then some extra libraries that are needed to Ignite. And probably the only one option that is really mandatory is a reference to the Ignite configuration, which will provide all those settings that are needed for Ignite pod to allocate memory and to connect to the Ignite service for the needs of IP Finder, and to start processing your queries. And that's all actually. So you just go ahead, you use this kubectl command to deploy your two pods in the cluster, and and in return you will get a memory database working in your Kubernetes environment. After that, it's up to you. Deploy your applications within Kubernetes and start using them all together with your distributed storage. But the more challenging thing is to support persistence. I do remember that, the first time when we developed this in-memory option for Ignite, we had several conversations with folks from Google who also was discovering, how can they support distributed databases with like disk-based databases for Kubernetes. We had a conversation at that time, like it was like Kubernetes was not that well developed. It was not well developed. I mean that it was mostly used for applications development, and some of the common configurations that are used today were missing there. But eventually, like let's say in a year or so, Kubernetes community supported stateful sets, and now stateful sets are used altogether not only for services and applications that need to preserve the state right during restarts, but also for disk-based databases or for memory-centric databases. And for Ignite, that's like also what we are using when we plan to use it as a memory-centric database, data on disk and in memory in Kubernetes. For that purpose, instead of Kubernetes deployment entity, we are going to use stateful set configuration. And there, what we need to do, we just need to provide some mount options to the place where our database files will be persisted, and then we just, depending on our requirements, depending on our use case and data size, we need to to accommodate the disk from our environment that is required to us. Also, for sure, like with many disk-based databases, the best practice is usually to separate disk for transactional logs or for write-ahead logs and for database files, so that they don't compete for their disk resources. And this is also can be easily utilized and supported with Kubernetes. You just request two different storage classes depending on your needs. One device, one storage is given to your database files, and the other is given to your transactional logs, write-ahead log files. And also, if you need, like also in Kubernetes, you can do snapshots for sure, backups, right? Also, again, you are creating a special storage class that is required, probably not that fast, not that, but anyway, so depends on the budget and depending on the requirements. With Ignite also, and with other many disk-based databases, after you just, once you deploy that stateful set, you again just getting your database created. And in addition, after, like, when we talk about distributed world, most of the databases require your administrators to activate your database, like if you use persistence, because there might be scenarios when, let's say, you have 10 machines in your cluster, and then you have the full restart, and after that full restart, you need to wait while every node joins the cluster, because if you activate your database too early, your application can start changing data, and while the other nodes are joining the database, your data might become inconsistent, just because some data was already changed and the other is still being kept on other nodes and they're not started yet. And for that purpose, usually many databases like Cassandra, like MongoDB, they give us special instructions so that once your database is up and running, you need to activate it. And the same thing you need to do with Ignite once it happens and running for the first time, so that after that Ignite memorizes all the nodes that were in our cluster, and after the restart of your full database, you don't need to do this activation if the number of nodes doesn't change. Once all the nodes that were activated the first time are up and running, your database will be activated automatically for you. And as for the management and monitoring, here is if to talk about Kubernetes in general, it depends usually on our deployment environment. Usually, if we deploy in Google Compute Engine or Microsoft Azure, or let's say in OpenShift, all of those tools go with special management and monitoring consoles, right? Also, we can use, usually we utilize a lot key Kubernetes standard dashboard that is available from open source. And whenever we talk about, but that will help us to monitor the Kubernetes piece. And when we want to monitor the database piece of our deployment, then usually we need to use the tools provided by the database vendors. On the Ignite side, we use Ignite Web Console. That just gives us all, 360 view on everything that is going on there. So I think that's all from the theoretical part. Let's quickly check the demo, how we can deploy Ignite with persistence enabled in our database, and then I'll be happy to answer the questions. So, what we are doing, so that we can save some time here and not be bothered by many switches. Let me show. I actually went ahead and before this event, I deployed my deployed Ignite in Microsoft Azure. So here is, if we take a look in here, I have my, it should be somewhere over here. We have my cluster deployed. It consists of 2 nodes. Let me check it. It should be over here. Yeah, so we have actually 2 nodes in our deployment. So I just prefer to use kubectl command. So we have 2 nodes in Microsoft Azure. Let's check it out. So they were deployed 8 hours ago during lunchtime, I guess. And then, as for the paths, I already have actually my Ignite cluster deployed there. So presently the cluster consists of 2 nodes in the terminology of Ignite. And that's actually what we can learn about Ignite from Kubernetes standpoint, right? But if you want to see what's going on inside of Ignite, we can use that monitoring tool. So this monitoring tool, you can deploy it whenever you want. In your own environment or in your Kubernetes environment. I'm just using the deployment created by GridGain. And so what I did, I also started a special application. We call it Web Console Web Agent. And this web agent sits in between my cluster that is deployed in Kubernetes and Web Console frontend that is deployed in some other server. And this is how I can connect from this web application to my Ignite cluster within Microsoft Azure and see what's going on there. So here as I can see those 2 paths on Ignite nodes deployed in Kubernetes. We have persistence enabled, some memory configuration, and etc. etc. So that's pretty easy and pretty straightforward. Speaking about the configuration, right? So if you talk about configuration of Ignite paths is also pretty simple. What we did, we just decided we are going to use Ignite of this version. That will be our configuration for Ignite. Some basic port numbers that we want to utilize from our applications. And that's like the piece that is related to the persistence. Here is I'm saying that I'm going to use one mount point for my write-ahead log files and the other for persistence for the database files, so that they do not compete for the bandwidth of our persistence. And that's the same, something related to their volume claims configurations. And that's it. After that, you start as many paths as you need, and your database scales in Kubernetes. Let's do the following. So let's see actually how we can scale our database. So for that, we don't need to come up with some special scripts or do anything else. We can use standard commands provided out of the box by Kubernetes. For instance, here is, let me copy and paste it. I have this command that actually tells that, okay, let's scale Ignite stateful set to 4 replicas. For us, it will mean that we are going to scale out our Ignite database from 2 nodes to 4 nodes. And this is actually what you can do whenever you just expect, growing workloads. For instance, that like Prime Day or Black Friday, you want to scale your database, you just scale out your cluster. Whenever the day is over, you can scale it in, right? So, and we're just using some standard scripts. So now if we take a look in here, let me see. I think that they're still being started by, Microsoft Azure. I don't know why, but for instance, in Microsoft Azure usually it takes, I don't know, 3 or 5 minutes to start one node, because like Microsoft Azure takes time, to allocate persistence for it. Usually it's much faster with Google Compute Engine or AWS, so that's something. We just need to wait. But this is, yeah.
Yeah, we'll wait for actual question. Don't you need another pod, which is the one for the auto discovery? Remember when you asked the Kubernetes service? All the pods that have the label Ignite?
Yeah, so that's the service.
Right.
So that's the service. I can show it to you.
Okay.
So that's it. And we call it Ignite. So every pod, when it starts, it just internally connects to the service, gets IP addresses to all the neighbors, and then it can join the cluster. Yeah, so let me just, that's how it looks like. And also like, okay, so we can monitor our cluster, we can deploy it, but let's try to use it. Now I'm just using my personal laptop. For instance, now let's assume that I'm at the development stage of my product. And my code is like, it's still like pretty, it's not mature. I don't want, to compile and deploy it every time in Kubernetes. But with Ignite, as with many other solutions, you can connect from your laptop, right? And I want to connect, let's say, using SQL interface. We are now reallocating in, let me see, reallocating in the bin folder of Ignite, so of that version. And I'm going to use that SQL line tool to connect to Ignite on this port number. So this actually port number is the address. This address is the external IP address of our service. So in addition, to that auto discovery or IP finder needs, we utilize the service, for like as our gateway to the cluster. And so the service will get this request and redirect to our cluster. So let's connect to our database. So we could connect to Ignite. And now I want to actually, let me see, I want to preload a sample database that is shipped with Ignite. It's just the database of all the countries and cities in the world with some numbers of population. So while it's being preloaded, let's check that what's going on here. Yes, so we created tables and also like caches is the same as tables. Caches in Ignite are the same as tables in the relational world. And like this database is tiny, just several kilobytes, but it's enough to do some calculations with it. So for instance, after that I can execute queries from here, from my laptop, such as select from what we have from city, all the cities, etc. Or if just all we need is to test some SQL queries, we can also go to this, we can use our web console. And here is I just predefined, I created an SQL notebook and I can run some queries. For instance, I want to find the most populated countries in the world. You have here China, India, United States, they're the 3 top populated countries. Also, we can do the joins, it doesn't matter. For instance, what are the top 3 most inhabited cities in countries such as United States, China, and Russia, and the rank is the following. We have, let me see, we have Shanghai, we have Moscow, and we have New York. And then like we can do updates, we can do deletes, and etc. etc. So actually this is how much time it will take you, to set up your, let's say, Kubernetes environment with your distributed database. Depending on your needs, you can use in-memory option only, or you can use disk-based option. And after that, once everything is set up, you don't need to wait while your application will be deployed there. You can directly connect to your deployment from your personal laptop, because actually Kubernetes and databases usually go for with all the facilities that help you to achieve this. And finally, what to say, if you're just interested in open source, we are looking for followers, we are looking for contributors, committers. If you'd like to contribute to Ignite, let's say to our SQL engine, to our computational MapReduce engine, to our storage, if you are curious about databases, about indexes, etc., join our community. Our community is growing pretty fast. For instance, like a month ago, Apache Software Foundation released the statistics where Ignite is ranked at the topmost, the most active, is ranked as the most active development community. We are the second most active user community, and also if to measure by commits number, we are not that far away from those vulnerable projects such as Hadoop or Kano. So all this means that we are growing, and please join us if you'd like to learn more about open source, or if you'd like to contribute to distributed databases such as Apache Ignite. So I think that I have 5 minutes to take your questions. So if you have any, please go ahead.
I just had a question. The console, the URL was console.gridgain.com.
That's like deployment of that console. Actually, you can. This is like what GridGain did, because sometimes you just want to demonstrate it, or you as a user, before installing this, the whole console is front end, back end, and web engine. You want to try it out, so you can start your cluster, let's say on your laptop, and use this console just to monitor it. But then, if you decide that you are good to go with Ignite, then you just take this console and deploy it in your environment.
Okay, so that was connected to Azure? Was it being routed to your Azure environment? Or?
Yes, so in that case, yeah, probably I didn't explain this point well. I have a special pod deployed in kubectl. Let me go before you. kubectl. We call it Web Agent. That's a special application. So imagine that here is on some machine in their network we have console.gridgain.com, that web UI. Then here is somewhere on Azure we have our Kubernetes deployment, and there we deployed that small software called Ignite Web Console. And that's like our gateway between the cluster and our tool. You just need to tell to that web agent during the startup that, let me show actually you that configuration. Doesn't matter. That, for instance, when you're deployed, just use that UI deployed on console.gridgain.com for monitoring and management purposes. In your case, if the part of web UI deployed in your environment, you just tell the IP address or in your environment.
Earlier you mentioned that bringing up Azure took 5 minutes, and that's kind of annoying. But I have a use case where I need to do heavy amount of in-memory processing, maybe for 10 minutes or 30 minutes. Then I need to bring the whole thing down. Do you have any recommendation on how to make sure that process is not just bringing the system out and down, and actually I can maximize the amount of space time for computing?
Yes, so for sure you don't need to bring it down, right? But your question is what to do if you need to scale it out, right?
Yeah, but only keep it for a short amount of time.
What I would do, I would just create some scripts that would just make use of standard Kubernetes commands. For instance, here is just I showed how to, by the way, yes, we now have 4 Ignite nodes up and running in our cluster. So I just used that stateful set command to scale out my cluster. But imagine that you created some script that would just fire in 10 minutes or in an hour and would do an opposite operation. It would go ahead and scale in our cluster. It would stop some nodes. This is actually what you can do, some automation.
So you don't have a recommendation on which cluster to use?
Here is it's up to your preferences. Some people, like I know that many companies, when we talk about private cloud deployments, many companies use OpenShift. When it comes, let's say, to public deployments with Kubernetes, it just varies. AWS for sure is the most popular option. I found Microsoft Azure is like pretty straightforward to start, at least for development purposes. But anyway, so I don't know. It depends on the strategy and taken in a company. By the way, how many of you are using OpenShift or any other public clouds with Kubernetes? Azure. And what's your experience? Do you like it?
So far, so good. Yeah, we haven't. No, like, Kubernetes we're only starting to use it now, but Azure we've used it in the past year.
Okay. No more questions? Thank you, folks. Thanks for attending.
Okay, everybody. Yeah, so I know some people came in during his talk, and just want to remind you that we're going to be raffling off some cool prizes over there, along with tickets to the In-Memory Computing Summit. It's October 2nd and 3rd in Burlingame, and it's going to be a great conference. Probably about 400 people coming in, experts from all around the world, including these guys talking tonight will be there. So it's a great opportunity to get that ticket for free. So I encourage you to use the tablet to sign up. There's also a link on the Meetup page as well. So next up is Roland. He's going to talk about databases and in-memory. Oh wait, that's sorry. Increase application performance and SQL auto caching with no code changes. All right. So take it away, Roland.
Thanks, Tom. All right. Good evening, everyone. My name is Roland Lee, and I'm going to talk about the concept of a database proxy. This will be very similar to a talk that I'll be having at the In-Memory Compute Summit in October. If I could get a show of hands out there, does anyone deal with SQL databases at all? Okay. Just you guys may deal with unstructured data, key value pair, and it may not apply to you. So just want to get a sort of a survey out there. What I'm going to be talking about is the concept of a SQL database proxy. Have you ever heard that term before? Anybody? Okay. It's not very popular, but it is used out there. It is gaining more popularity. So I just want to share, I'm going to spend about 15-20 minutes maximum sharing with you about the concept and why people use a database proxy in between the application and your existing SQL database. And I'll open up for questions. Okay. So in this slide here, this is about a web application. And one of the problems or challenges of web scale is that as you grow more users, the application tier grows, higher data volumes, more tables, more changes to schemas. You all know that. But what's often missed is higher latency between the application database. And what we found is that's often neglected, which causes poor application performance. And the application developer or NetOps really needs to make note of how do you solve that round trip time, especially if the application is very chatty and there's poor SQL going to the database. That's going to slow down the application performance. Oftentimes what I see, because I come from more of an application networking perspective, there's a lot of emphasis on the front end. So a lot of caching of HTTP, a lot of CDNs, but not a lot of optimization on the back end. And I think that's where what we're talking about, like in-memory computing. How do we make getting the data faster and crunching it? So in this slide, I'm going to show you some vendors out there today that are database proxies. To my left, your right, has anyone heard of Proxy SQL? It's an open source MySQL proxy. And it does a few things. It does automated failover for you. It does SQL read-write splitting. So, and then there's MariaDB, which is in this building. Okay, they have a product called MaxScale, which is open source. They do same thing, automated failover, SQL read-write splitting. Now, there's two proprietary products, Scalark and then Heimdall Data, which I represent, which is going to go open source. We do a little bit more, and I'll talk about some things that we do differently. But why do this? Okay, why use a database proxy? The reason why is this offloads a lot of the work for which a backend developer would have to do, such like be concerned about failover, making sure that the database is redundant and that if a failure were to happen, how do you fail over gracefully? Read-write splitting. Has anyone heard of that term before? Read-write splitting. What read-write splitting means is that unlike HTTP, which is stateless, databases obviously are stateful. So when there's a write query, it needs to go to the write server. And the read query needs to go to the read server. So the application needs to know how to route it correctly. So what these database proxies do is that it routes the queries to the right servers for you, so that you don't always have to modify your app. So if you add another read replica, or you add another write master, you have to modify. You typically have to modify your application to do that. Now you don't have to do it. It's transparent. It's just a policy on the database proxy. Make sense? Okay. What Heimdall Data has done is it's combined a bunch of things: Proxy SQL, New Relic, which is like application performance monitoring, some failover, and it's created a database proxy that doesn't require any code changes. So there's no development necessary, application change necessary to use this product, and it's also database vendor neutral. Most all database proxies are like this, except they tend to, most of the other ones tend to focus on a particular database like MySQL. In this case, Heimdall Data is database vendor neutral. It's any SQL database. And the way that it works is that there's two software packages. If you are JVM based, anyone who's JVM based JVM based applications? Okay. If I explain it to you, then you'll understand why it's not, it doesn't require any code changes. To your right side, Heimdall Data acts as a JDBC driver. Okay? So what you do is you shim in the driver in between your application and your current JDBC driver. So you just change the class path, the URL, and you're done. It's a 5-minute install, and boom, you're going to get all those types of features. If your application is not written in Java or Scala or Go, it may be Perl or Python or whatever, there's proxies like that runs as an agent. It's basically a sidecar container, if you will, and there's a MySQL proxy, a Postgres proxy, a SQL Server proxy. So any of these packages allow no changes to your application nor your database. Any questions here on this type of packaging? This is very common to a database proxy, whichever proxy you use. So there's no code changes. Now I want to talk to you about a little bit about what a proxy does, go a little more in depth. What it's doing is it's basically a data access layer solution so that you don't have to develop it. And one of the ways that it offloads the database is that it provides caching. So it's caching SQL results. And what Heimdall Data does is it automates caching and it automates invalidation. If you know, cache invalidations in computer science is one of the most difficult problems. It automates it. So you drop it in, and it will automatically cache the SQL results, the queries that's going to provide a performance benefit. And upon a write to the table, it will automatically invalidate. Make sense? So offloading the database and providing faster performance. But what makes this also unique, not only does it auto-cache, but it's caching at the application tier. So that's where it avoids and solves the network latency issue. It's optimizing SQL from an application perspective. So all the queries that would have gone to your database, the database doesn't even see those queries because it's being served out from cache. And here's what I want to talk about in terms of how does this database proxy align with in-memory computing, okay? GridGain, Redis. Well, if you have a greenfield, I think if you want the best performance control, by all means write the app to an in-memory database, right? But let's say if you had a legacy database, and if I can tell you through a database proxy, I can get you I can get you 70% of the performance without any changes to your application. Then you may reconsider rewriting your application, right? If I can say I can get you 70%. So that's one thing to consider rather than just going straight into, let's say, in-memory database. You may want to keep your current infrastructure and look for ways to optimize it without modifying the terminal. Okay? Secondly, you may not be familiar with in-memory computers using Redis or GridGain. This is one way of sort of, if you will, dipping your toe in the water and familiarizing yourself with some of those components. But you're not going to use it as a system of record, as a database, but you're initially going to use it as a cache. And that's what I want to talk about here. What Heimdall Data does, or even Proxy SQL, or any of the database proxies, is that it is going to automatically cache into the cache of your choice. So Heimdall Data, the database proxy, isn't selling cache, but it's providing the logic. So you choose the grid cache of your choice, GridGain, Hazelcast, Redis, Oracle Coherence, you name it, Memcache D if you want. What the database proxy will do is the caching logic and the invalidation logic that will choose which queries to cache into the cache of your choice. Okay. Does that make sense? So as I mentioned, there's no code changes, so it applies to third-party applications for which you have no control over the code, or it can be custom code. So let me get to the architecture of how the database proxy works. It's a one-to-one. So for every application instance, you're going to have a database proxy in the application instance. So it scales very, very nicely. So if there's 3 app servers, there's 3 database proxies. And the way it caches is that, again, it's going to choose which queries make sense to cache because it's frequently asked, and it's not changing. And it's going to cache into, in this example here, is caching into GridGain. And upon a write to the table, add, insert, or delete, the proxy will use GridGain to communicate to all the local caches to invalidate that table. It's all done automatically. So if anyone has any experience with caching, it's very complex. You need to, the difficulty is in validation or keeping the data fresh. You have to set the TTL, the expiry. You don't have to do any of that anymore. The logic in here determines what you should cache. You can add more cache rules, you can delete more of it, or you can just rely on the logic here to cache and invalidate, which is pretty cool. I mean, we did a survey and we found out that creating a cache system and maintaining it takes developers 20% of a developer's time a year. So that's 1 day out of the week, just to maintain and create a cache subsystem. Now you can do that in 5 minutes. Just click of the button and just not deal with caching anymore, but focus on revenue generating features. Not only do database proxies cache, but they can also do failover. So database proxies are SQL aware, so it's not this IP type of or TCP based failover, but it's SQL aware failover. So it detects the health of a database. When it deems it as unhealthy, it will hold the connection, buffer the connection, and gracefully fail over to the redundant database. Let me talk a little bit more about caching, just go a little deeper, because it's I think it's quite interesting. The idea here with the Heimdall type of caching, it's sort of a L1, L2 type of caching. It's for every application instance, it's going to cache at the local memory of the application server. So you might think, well, isn't that, you have enough memory? Well, it is application dependent. In our experience, it's only taken probably about 50 to 250 megabytes to cache the hot objects. The remaining data that you want to cache will go into a cache of your choice. Okay? And it's really the L2 cache that communicates via pub/sub to the local caches upon any update to the table, any write to the table. So we use that as a messaging bus to do any validation. So you have a level 1 and level 2 cache. So if you're caching from the application, just think about how fast the response times are. The application thinks that it's talking to the database upon a read, but it's being served out from in-memory locally. That's pretty fast. And the other benefit that you're doing too is that it's offloading the database. So if you have a commercial database, you're saving hardware, you're saving licenses, you're saving costs. So there's a lot of benefits of caching SQL, doing optimizations on SQL from an application perspective.
Can you configure the size of the local cache?
Absolutely.
So you can, if you don't want to spend too much memory in JVM, you can push more of it to say Redis.
Absolutely. The question was, can you configure the heap size, the memory size? Absolutely. It's all configurable to what you want to do. But it's typically 50 to 250 megabytes. So I don't think anyone's going to be very concerned about this. We're not talking about gigabytes here.
Okay.
But for some applications, it could be very large. So you do need to make note of it. Okay? So we have this L1, L2. Any other questions about this? Any feedback?
This is a JDBC driver. Is it in the Java? Is it on heap or off heap? Is it cache?
Okay. It's on heap. It is a JDBC driver, but it doesn't have to be, right? It could be that's one of the software packages as a JDBC driver.
Mm-hmm.
But if you're not JVM based, you can just use a sidecar process. It's just a proxy. So there's different packages. Okay. So if you're not using Oracle, if you're not, you may use SQL Server. It's just a SQL Server proxy. It runs as a separate process. It's an agent on the app server. Okay. Any other questions about packages? Okay. And again, I just put a bunch of cache vendors here. We work with all of them. GridGain as well, Coherence as well. You choose the cache of your choice, and the proxy will just add the caching logic and the validation logic. Okay, I think I mentioned this already. Writes go to the database, reads go straight into the cache and get served out from the local and L2 cache. This is how it works. Basically, high-level data intercepts and forwards the SQL traffic between the application and the database. High-level caches SQL results only if it provides a performance benefit. So it's not going to go to the cache to L2 cache if it knows that it's going to be a cache miss, or that's going to be a double whammy, right? Just think about it. If the application does a read, it goes to GridGain for the read, but there's a cache miss, then it has to go to the database. We're talking double round trip there. Not a good thing. So what's going to happen is we have keys that know that if it's not in GridGain, it's going to go straight to the database. Okay, so you save that network latency. Just to be clear, it's a simple SQL results cache. It's not a write-through cache. It's not a read-through cache. When it sees that query, that exact query, it will serve the results out from cache. It's that simple. Okay. So it's not. We're not writing SQL into GridGain. It's just a key values pair where the key is the query and the value is the results. Okay.
So on that comment, right? So if I first do a query that retrieves a lot of stuff, so that gets cached, then I say, well, I want to filter as an end user. So I say the same query with an extra condition, right?
Yeah.
Where something else. So it is technically a different query, right?
Yes.
It will go to the SQL database in that case, and all the information is actually in the query.
Yes. So the question was is that if the query has any types of variation, is the logic such that there's some flexibility of saying, oh, those are the same result. That would equate to the same result. And the answer is the query's got to be exact.
Okay.
And we do that because we want to be safe. Okay. Data integrity is the most important. Performance second.
But that's a typical use case, right? When you are drilling down, right? You get a bunch of information, you do some analysis, and then you say, I'm going to drill down and I do a filter on top of what I did before, right? That extra filter, it will, it's unfortunate, right? All the memory is in the data, all the data is in memory, but we're going to go back to the database.
Right.
Yeah,
So
not necessarily.
yeah. So what's going to happen? The way it works is that it's going to hit the database at least one time, and after the subsequent time, because we've cached everything afterwards, because we got the result, and we'll cache everything else, and subsequent queries, selects, will be served out from cache.
Right, but it's a different query, right? Because every filter I apply,
Yeah.
I'm putting an extra condition on the SQL, right?
Yeah. So
that is
correct.
syntactically a different
if it's
statement.
syntactically different, if it's gone to the database once, we'll have it cached the second time.
Okay.
The second time.
Okay.
That's my point. Yes.
Earlier you mentioned you expect 70% gain. Can you walk me through kind of what use case you would get that 70%, that basically every other query you're able to hit the cache?
Yeah, let me give you some generalizations. We found that in our use cases that we've seen, especially for web applications, web scaling, we've seen cache hit rates anywhere from 30 to, and I'm not kidding you, 95% cache hit rate. A typical application would be like Odoo, which is Postgres based. We're getting like 92% cache hit rate. So that means 8% of all traffic is hitting Postgres. The other 92% is being served out from the application to it. That's pretty good. That's, now you're really going to scale the database that way. And you're going to save costs, and then the application response times are going to be real fast. Mileage will vary based on the type of use case, but for web app e-commerce, which tends to be very read heavy, which tends to web scale the application tier, this is database proxies are very ideal, so that you don't have to build it, you just deploy it.
Was it 92% for the local cache, or it was for the complete cache?
For the complete cache. Yeah. But the majority, if not all of it, was being served out from the local cache. So it's a long tail, and the hot objects primarily get the hit. Typically, just to be clear, the L2 cache primarily is being used as a message bus to communicate to the local caches that there's been an invalidation. But it also serves as a level 2 cache as well. Okay? We're okay? How am I doing on time? I don't want to.
About 5 minutes.
5 minutes, okay. Let me get through a couple use cases, and then I'll entertain some questions. So let's talk about horizontal scale up. After you've scaled, your database is overloaded. You first want to vertically scale up, so you're buying more CPU, buying more memory to scale up, and that has a ceiling. The next solution is to scale outward, scale horizontally. And what you typically do is have a write master. You separate the writes from the read, so you have a write master and read replicas. Does that make sense, guys? And when you do that, you typically have to rewrite the application to route the queries. Well, you don't have to do that anymore, especially if you have no control over the application. With a policy on a database proxy, you can say, well, when you see a write, it goes to this write server. When you see the reads, go to these reads and load balance across the read replicas. So that whole logic of read-write splitting or read-write routing is taken care of in a database proxy. Okay? Any database proxy supports this. We do have something unique. Would love to get some feedback since we're a Meetup. We have a feature which is called replication lag detection. And this is a problem that's often neglected. Think about a read followed a write. Let me see. A read followed by a write. So you do a write, and then you quickly do a read. Oftentimes, the data hasn't been propagated from the write server to the read. So what happens is you get non-fresh data. So what we've done is we have lag detection of a window, and we've calculated when the data has been propagated from the write server to the read replicas. So if there's a read, and it's within that lag window, that read is going to be read from the write server. until it falls out of that lag window, then I'll read from the read replicas. Does that make sense? This is logic that you typically have to put in, and it's a pain, but this is something that we have as well, the lag detection, to ensure fresh data upon a read. And again, this read-write splitting requires no application changes. Let me just end with this use case here. Does anyone deal with data analytics at all? Data warehousing? What type of vendors do you guys use? Throw some out for data warehouse. Redshift? Any Pivotal Green Plum? Netezza? Or Teradata? Well, let's talk about Redshift. Obviously, there's performance issues with Redshift with frequent queries, because typically, it's using MPP multiprocessing of large data sets. And one of the things that a database proxy can do, again, is routing. What it's going to do is it allows the support of mixed traffic of OLTP and OLAP traffic. It's going to see what type of traffic it is, and if it is OLAP traffic, it's going to route it to your data warehouse. But if it's OLTP transactional traffic, it's going to route it to a garden variety, for example, Postgres transactional database. That's a big deal, okay? Because what it's going to do here is that Postgres data will batch DML operations and send that to your data warehouse as a batch DML operation. It can also manage materialized views, because Redshift, for example, doesn't support materialized views. So it can act as a manager of materialized views as it offloads the OLTP traffic. So this is a very, very interesting use case, which Amazon has going to write a white paper for. But this is what a database proxy can do too. And we've seen performance gains not of 70%, but up to 100 times. Okay, because these frequent nuisance type of queries can be offloaded to another database, in which it will, on a separate thread, communicate through data federation back to the data analytics store. Yes?
The decision making when you get a query to decide analytics or OLTP, is tactically analyzing the statement, or?
Yeah. It's rules based.
Okay.
Yeah, and it routes it. So we can do routing, batching of DML operations, better management of materialized views. It takes a snapshot. Rather than asking for 20 years of data, maybe you just want the first year of your sales data, right? Postgres will have that quote-unquote cached of just that year instead of going to Redshift. So that speeds up the response in data set so much faster.
So it's transparent to the data consumers, right? They don't
Absolutely.
Okay.
So database proxies are transparent, no code changes. It's just a drop-in. Right? So there's a lot of other use cases, but I think my time is up. But I just want to give you a flavor of why you would use a database proxy with these use cases. And again, how does it help out with in-memory computing? If you haven't, if you're not familiar with in-memory computing, rather than using it as an in-memory data store, you may try out GridGain or Redis just as a look-aside cache first. Try that out. See what gains you get. If it hits 70% or 50%, if it's good enough, that might be just good enough for your legacy application. But for greenfields, you might want to just start from scratch, and that's why you don't need a database proxy. You write straight into GridGain. You'll write straight into Redis. Thank you.
Thanks, Roland. Now, Sam's up, Sam Drake. He's going to talk about what makes an in-memory database different. Is that right, Sam?
Yeah.
All right. And as Roland's mentioned, you can use GridGain or Apache Ignite. GridGain's also free. You can download it free for the first month. It works, even the enterprise version. So give it a whirl, or just go right with that Apache Ignite and check out Roland's his stuff there. I think it's pretty cool. Sorry, Sam, to leave you.
Un momento.
And if you haven't registered, we've got tickets to the In-Memory Computing Summit once again. I encourage you to go Google that and check out the, I'll put, it's on our Meetup page, but going to be some great stuff. Sam will be there as well.
Heck yeah. Can everybody hear me okay? Yeah. Okay. Thank you, Tom, very much. I really appreciate it. And hi, everybody. Thanks for coming out. My name is Sam Drake. I'm architect of Oracle Times10 in-memory database. Times10 is one of the very first in-memory databases on the market, and it's, I'll tell you a little bit about it. I haven't spoken at this meetup before, but I gave a speech a few months back at the same meetup in New York. And one of the questions I got then was a real basic one from the audience, was what makes an in-memory database different than a traditional database? I thought that was a great question and a good place to start. So, you know, we can talk about use cases and scenarios and all of that, but let's sort of, what I wanted to do today was really just sort of start at the beginning. You know, how many of you are using an in-memory database today? A lot of people, great, great. Which ones? Just call out some names.
Ignite.
Ignite, well, yes, of course. Anything else?
Geo.
Okay,
In Quarter.
okay, cool. Well, so I'm going to talk a little bit about what an in-memory database is, and I'm going to say right up front that my background is from the OLTP side of the world, right? Using in-memory databases for transaction processing. You know, analytics is a different thing. Times10 can do analytics, but I'm going to come at this from one angle and a kind of a cranky, biased old guy angle. So if you don't like my definitions and you think I'm wrong and you want to get into a fist fight about how I define some term, that's great. But you know, fine, you're right and I'm wrong. I don't care. Since I work for Oracle, I have to put up this slide, and this slide basically says everything I'm going to say is a lie. So don't believe anything I say for the next few minutes, and we'll all be good. I did want to say just a little bit about, this isn't a talk about Times10, but just what in the world is Times10? I have to have some reason to tell my boss I came here. Times10, as I said, is one of the very first in-memory databases. It was developed as a research project at HP starting in 1994, spun off as a separate company in 1996. I was employee 6 of that company and I'm still working with Times10 today. It was acquired by Oracle in 2005. It's used, Times10 is, nobody here is using it Times10, and I'm not surprised, but the reality is that more than 1 billion people around the world use Times10 every single day. Times10 is probably the #1 database used to do telephony billing around the world. If you've ever used a prepaid mobile phone, chances are you've used Times10. It's also used heavily for things like stock trading, transportation, logistics, e-commerce, and those sorts of things. Again, with an OLTP focus in environments where response time and throughput are absolutely critical. If you think about how many text messages per second are sent in China, for example, it's a lot, and we don't bill for all of them, but we bill for a huge percentage of them, for example. Times10, the current release of Times10 is Times10 18.1, and the Times10 can be used in a number of different ways. It can be used as a database of record. It can be used as the only database in your application. It can be used as a cache in front of Oracle databases. And so we continue to support those ways of using Times10. Until this release, Times10 has always been limited to running on one machine or maybe a replicated set of machines. Starting in this release, Times10 is now a fully shared nothing scale out database. So if you want to run a single in-memory database that distributes across 32 or 64 machines, you can do that with great scalability. So just a little bit about what we are. And that'll sort of set the tone for my cranky set of biases, which I'm going to inflict on you for the next few minutes. So we're going to talk just a little bit about really just basics under the covers of what is an in-memory database and how is it like and different from a traditional database. And if this is obvious, I apologize for having another beer. So let's start with what is an in-memory database. This is a really simple slide. An in-memory database is a database that was designed from scratch assuming all the data in the database fits into RAM, right? That's it. I mean, that's really all there is to it. You know, it's a database designed assuming everything fits into memory. And there are lots of other things. You know, there are databases that are called memory-centric databases or hybrid databases, where maybe not all the data has to fit into memory. By my cranky biased set of definitions, those aren't in-memory databases. An in-memory database is one where all the data fits in RAM. And they've designed all the algorithms assuming that. And as you'll see, that makes a huge difference. Now, why do you care about whether a database is in memory or not? Well, in-memory databases are really fast, right? Everybody knows disks are slow. Everybody knows flash is pretty fast. Everybody knows RAM is a lot faster than any of those things, right? So it stands to reason that an in-memory database should be really fast, and in fact they are. How fast are they? Well, every vendor will give you different numbers, and we could compete about, you know, argue about artificial benchmarks that have nothing to do with your applications. Here are my artificial benchmark numbers that have nothing to do with your applications, right? You know, for the way the times 10 classic, where times 10 is deployed on one or two machines, the focus of that set of use cases is response time, right? If you need to execute SQL and get the response back with the absolute minimum latency, we can do that better than any other database on the planet. If you need to handle a SQL select in less than 2 microseconds, 2 millionths of a second, or a SQL update in about 5 millionths of a second, through standard APIs and standard interfaces with standard SQL and no magical tricks, we do that, right? So that's pretty fast. In the scale-out version of the product, the emphasis, because there is inherently networking in connecting all those machines together, the focus is more on throughput. We still give great response time, but not as fast, because there is sometimes some network traffic involved. And in a single database in memory, we can do over 1 billion selects per second. So again, pretty fast. Again, through standard APIs and interfaces in an application that would have worked just the same if you connected it to the Oracle database if you just changed one line in the configuration file. And that's pretty fast. Is that Bert or Ernie? That's Bert? Okay. All right. Bert's amazed. Tell me again why SQL is too slow and you've got to rewrite your application to use NoSQL. You don't. There's no reason, you know, if anybody tells you you have to abandon SQL for performance, they're wrong. Okay, so that's my definition of what an in-memory database is. I've been doing this for 22 years, but your definition may be better than mine. So how is an in-memory database like a traditional database, and how is it different? Well, let's look at well, first of all, an in-memory database, as I said, is a database, right? Now, databases are all over the place, right? Some are SQL-based, some have key values, some have XML, some have networks. There are all sorts of data models and all sorts of ways people want to think about their data. But hopefully every database that can call itself a database has at least some passing relationship with what are called the ACID properties, right? And those are really what make a database instead of a data manager or a cache or something else, right? And the ACID property, how many have heard of the term ACID properties before? Right? Yeah, I'm sure everybody mostly has. And so ACID is an acronym, stands for atomicity, basically meaning can you run transactions? You know, can I subtract money from your account and add it to my account and commit that, and either the money's in your account either at the end of the day the money's in your account or in my account, but it's not in both of them and it hasn't been lost, right? It's amazing how many things pretend to be databases but can't do that basic thing of I want to transfer 20 bucks from you to me and make sure it really doesn't just disappear. That's atomicity, A. C is consistency. Can you have constraints, right? Can I, if a customer placed an order and I delete the customer, does the order still does the order get deleted too, right? Just basic things like foreign keys and constraints. Is the C, I is isolation. Can we both make changes in isolation? It gets into repeatable read and all of these isolation modes you've heard about. And D is durability, right? That's persistence, right? Can't be a database unless you can actually store my data, right? Things that lose your data probably aren't really databases. Now this is where everybody gets confused. I've talked to a lot of customers over the year and a lot of prospects over the years. And people's heads sort of explode at this point. Oh, I gave it away. If it's an in-memory database, right, RAM isn't persistent. And so you're going to have an in-memory database that's persistent. How in the world do you do that? A lot of people think you can't. People say just assume that an in-memory database goes away when you turn the power off. But that's just not true, or at least it doesn't have to be true. And I would argue that if it does that, then whatever the thing is you're using isn't really a database, it's something else. So, again, head explodes, right? It's all in RAM, but it's persistent. How in the world did that happen? Well, so let's think about those sort of metrics. And again, every vendor can put up their slide saying how well their product matches up to those. Our product is a pure SQL database, uses Oracle-compatible APIs, interfaces, data types. You can use the exact same set of tools and techniques and languages and APIs and interfaces and code that you would use to talk to your back-end database can talk to your in-memory database. Somebody talked a few minutes ago about how maybe you don't want to rewrite your application just to use an in-memory cache. Why would you have to? Why doesn't your in-memory cache speak the same APIs as your back-end database? Of course it should, from my perspective. Okay? Timestamp has full transaction support. You can insert 1 million rows and then you can do a rollback and we'll forget about the 1 million rows you just inserted. It supports real transactions without limit. You can transfer money from your account to my account and we won't lose the money or double it. Has constraints, has isolation, and it has durability. Durability comes in a number of forms. We actually store transaction logs on disk. And with various degrees of synchrony, right? If we're trading stocks where a transaction might be worth $1 million, guess what? We're going to write that thing to disk right away. If we're billing for text messages, maybe we won't. Maybe we'll wait a little while before we bother to write that to disk. Because if the system goes down and we forget to bill 20 people for 20 text messages, here's 10 cents, big deal. Doesn't matter. And so customers can make that choice as to how much they care about durability versus performance. We can also replicate the data to other machines. In timestamp scale-out, you can control how many copies of data we keep, so we can automatically keep 2 copies of data, for example, on 2 machines, just magically. So that's kind of how we match up here. Naturally, we match up pretty well. Other vendors probably, would probably argue that, probably do too, some probably don't. Okay, so now any questions so far? Just real quick? No? Okay. So now the question is, how is an in-memory database different than a traditional database? And if you look under the covers, they are different. First, let's start by talking about the architecture of a traditional database. So you've got a set of applications connected over a network to a database server. The database is on disk, and there's some sort of an in-memory buffer, an in-memory cache, right, that the database keeps of recently used chunks of data, right? And so some of the data is in memory that is kind of faulted in as in some sort of an LRU, least recently used cache of disk blocks from that disk. And so let's say that there's a row and a table down here that describes me. It's kind of a scary thought. That's on that disk. So, PowerPoint animations, right? So somebody does a select looking for my records. That goes over the network, of course, to the database server. The database server then looks in its in-memory cache to see if my data is in that cache, right? Nope, it's not there. Well, that's fine. Then it's going to go off to disk, see if the data is there. Oh, yeah, it is. And of course, it'll cache a copy in memory and send a copy back to the application, right? So the second time I query that, anyone queries my row, it's probably in memory. This is not rocket science at all, right? So how's an in-memory database different? Well, not a lot at this level. You know, you still have applications which talk over a network to a database server. You probably still have a copy of the database on disk that's more or less up to date depending on the product. You might also have applications which are more directly connected to that RAM and can use that database without going through that database server. Times 10, for example, supports what we call direct mode, where an application that runs on the same machine as the database can use the same standard SQL and same APIs, but doesn't have to go over a network, doesn't have to send a message. It can just look straight in shared memory under the covers, find your data, and return it to you with no context switches, no messaging, no round trips, which makes it run a whole lot faster. But basically at this level, the architecture is pretty much the same between an in-memory database and a traditional database, right? The big difference is the database in memory is the same size as the database on disk, right? Remember, an in-memory database assumes all the data in the database fits in RAM, all of it, not some of it. That's a hybrid database or a memory-centric database. An in-memory database stores all the data, it assumes all the data fits all the time. But you know, when we get down to the, so my data, you know, is out on disk somewhere, but it's also always in RAM. And so somebody issues the same select, it goes to the database server, they look in memory, and it's always there, and so it gets returned back. That's faster. Right? So an in-memory database is faster. Well, you're probably thinking ahead and thinking, well, but I know how to fix it. I don't need an in-memory database for that. I can use a traditional database for that. So let's, you know, you're thinking, okay, yeah, I've got a disk-based database. You know, that was a cute trick he just showed, but it wasn't really all that hard. All I need to do is make my in-memory cache bigger, right? I'm going to make my in-memory cache in my traditional database the same size as my database. You know, if I've got 10 terabytes of data here, I'll just have 10 terabytes of data there. It's a pretty big machine, but okay. And magic, I can use my old traditional disk-based database. I don't need an in-memory database. Well, no. You know, so in that environment, everything's cached in RAM, right? So you know, maybe the first time when the system starts up, it's not there, but after that, Sam's in memory, and he's going to stay in memory forever. Magic. I'm going to get the same performance as an in-memory database, right? No, you're not. Even I can read his lips. So why is that? Why isn't that the same speed as an in-memory database? Well, now we have to look a little bit different, in a little more detail of what's inside of that in-memory buffer. Now, in a traditional in-memory database, a traditional database, not an in-memory database, in a traditional database, what's in that memory is really, as I said, a cache of blocks of data from disk, right? So the first time a block is read, it's read and stored in the cache, and it's kept there for as long as they can keep it. And the next time somebody needs to access that block of memory, they access it out of there. So let's kind of animate our way through that, right? So let's say we have an index, and we've got this in-memory chunk, this set of buffers that are cached copies of blocks from disk. Well, we also have to have this thing called some sort of a cache directory, right? You know, which blocks from disk are in here and where are they, right? You have to keep track of that, right? So, so every time you look for a row, you have to do 2 searches, right? We're trying to find Sam's row, which is somewhere in that disk block. So we have to look up Sam in the index, figure out, and the index might say, well, Sam's row in the emp table is on disk block 1, 2, 3, 4, right? So that's one lookup we had to do. Well, where's block 1, 2, 3, 4? Now we have to look and see if 1, 2, 3, 4 is in memory. So then we have to look in the cache directory. Hey, is 1, 2, 3, 4 cached in memory? Well, it might be and it might not be. The software wasn't written assuming all the data fits in memory all the time. So even if that memory cache is exactly the same size as the disk, it doesn't know that. So it still has to do that lookup. And the directory then comes back and says, yeah, there's the address of that Sam guy. And then you can just dereference a pointer and get to my data, right? But you had to do 2 lookups to do that. Well, in an in-memory database, right, an in-memory database, remember, the definition of that is designed from scratch, assuming all the data fits in RAM all the time. So we don't have to store disk blocks in our index, right? We can store pointers in our index. And so this application comes along, the application comes along, forget all the animation, it wants to find Sam's row, looks in the index says, yep, it's at this address, and then the database engine just goes and looks at it. It seems like a simple thing, but what it means is you can save hundreds of instructions every time you touch a row. Now imagine you're joining 2 tables together, right? A single simple query might touch 10,000 rows or 1 million rows, right? That's 100 million instructions we saved, right? Just by doing 1 lookup instead of 2. So that's the speed up of an in-memory database. It's designed from scratch, assuming everything fits in memory all the time, so you can simplify those algorithms. So why is it faster? Oh, they're cute. Is an in-memory database faster because it reduces I/O? What do you think? No. Because remember, in that case, right? If my in-memory buffer is the same size as my database, once I load the whole database into memory, I'm not going to do any reads. I'm never going to do any disk reads, right? Correct? I'm never going to do any disk reads, correct? Everything's going to be in memory. I'm going to do some writes, maybe to log it to disk to make things persistent, but I'm never going to do any reads in a traditional database or an in-memory database. You can achieve that advantage of reducing I/O with a traditional database and a lot of RAM. Okay, so why is an in-memory database faster? Well, an in-memory database is faster because it can use simpler algorithms to do the same thing. I don't have to do 2 lookups, I can do 1 lookup to do the exact same amount of work. Less CPU time is good, gets the seal of approval. I apologize for all these animations. I don't know who did this, so okay, I guess I did it. There is actually less I/O. You really don't do any disk reads at runtime, but you can achieve that with a traditional database too. You could achieve that with with a 40-year-old disk-based thing you found lying around. Disk speed still matters because you still have to log those transactions and make them durable, but it doesn't really matter, right? An in-memory database isn't faster because it eliminates I/O, and anybody who tells you it is kind of missing the point. An in-memory database is faster because it uses less CPU to do the same amount of work. Any questions about that? No? It was all obvious? Have another beer? Okay. Just a couple more slides and we'll get you out of here on time. I titled this section, Using an In-Memory Database. What do I need to do in order to use an in-memory database? And from my perspective, the first question you have to ask, and this is why I work in architecture, not in marketing. The first question you have to ask is, do you need one, right? And honestly, a lot of people don't. If you've got an application which has users sitting at terminals and they're going to type in some data and push enter, and you want to have that mythical sub-second response time, sub-second's not real hard. Maybe you don't need an in-memory database to do that. On the other hand, if you're trading stocks, right? The price of IBM goes down, and if you, anybody from IBM here? No? Okay. Price of IBM goes down, and you, if you react to that trade, to that price change, and you buy it or sell it before the other guy does, you make a lot of money, and the other guy doesn't. Response time's all that matters there, right? And those things are done by computers, not by people sitting at terminals. And so if you're 100 microseconds faster than the other guy, you win. right? That's an environment where microseconds matter, millionths of a second matter. Maybe you really, really couldn't possibly go without an in-memory database. Of course, you have to think about, can you separate out the subset of your data that you're going to store in RAM? You know, you're probably going to really have another disk-based database, Oracle or something on the back end that holds everything. So you just but can you separate out the set that really needs to be in memory? You also have to think about your read-write ratio, right? If in-memory databases do speed up writes, even if they persist them to disk, just because it's a lot faster and more efficient to find the data that you want to change. But they speed up reads profoundly, right? And so, the more reads you do, the more benefit you'll get from an in-memory database. Right? You'll get benefits even if you do a lot of writes, but you'll get a lot more benefits if you do a lot of reads. And you have to think about your durability requirements, right? If you're trading stocks and every time you record a trade, you have to write that on 3 disks and store it in 3 memories, otherwise the government's going to come after you. Well, all that networking and all that disk I/O is probably going to be the critical path, right? So you have to think about all those things. And in-memory databases can be useful in those environments, but you won't get those magical numbers that the vendor would like for you to think you would. So what do you need to do in order to take advantage of an in-memory database? I've been a developer, a consultant, I've been the product manager, I've worked with a lot of customers over 20 years. I gotta say the number one thing you've got to do is fix your apps, because your apps suck. People do really silly things, like have their application connect to the database every time they want to execute SQL. It's nice that I can execute that SQL in a microsecond once it gets over there, but it's going to take 1,000 times longer than that to establish the connection in the first place. And that's true for any database. So, use connection pools. Don't have silly apps that come and go every 100 microseconds. That do one thing and then disappear. Right? Have the application stay around for a while. Back to the previous talk, right? Use bind variables, right? If you're executing SQL like select star from emp where name equals Sam, and then you're going to turn around a few seconds later and say select star from emp where name equals Sally, that's, every textbook about how to use SQL will say that's the wrong way to do it. You say select star from emp where name equals question mark, and then you pass in the name, the name in a bind variable runtime. Right? Use a sensible programming language, right? How many people think Java is the same speed as C? Good. You're all smart people.
Not so far behind.
Okay. Good for you. This is the one I just said, prepare SQL. Networks are dog slow compared to RAM. Networks are horribly slow. And they use a lot of CPU. Just sending a message back and forth uses a lot of CPU. Yep.
But doesn't that make kind of the whole thing, a lot of the in-memory database advantage disappear if you're doing the scale out, because then you basically going through the network, it's not as simple.
A lot of it does, and that's there. A lot of it remains, but that's why I was very careful to say in the what I call the classic ways of using ×10, we can give you those microsecond response times, and we sometimes can in the scale out version. If the application and the database and the data you need are on the same machine, this performance is the same. But if it's not, you're going to go over a network, and yeah, it's going to dilute some of the advantage. And so the game changes. For us, it changes from pure response time to throughput. We can provide huge benefits there, but it's a different world. And we can also provide, and I think most databases do, scale-out databases do, they give you some way that applications can kind of get some idea of where the data probably is. So if they can steer things in their application to the right node, if I knew that all the phone numbers in 408 area code were all stored over here, and I could arrange to send those billing requests to those servers in the first place, then the database could really run at those memory speeds, right? But yeah, networks are slow, and if you're going to use a network, you kind of got a problem. and so the next bullet was going to be you really need to move your apps closer to your data, right? There's this 3-tier model for how everybody ought to write applications. You've got a database tier, and then you've got an application tier and your presentation tier, which I guess are web browsers. That is the worst possible model for performance, right? It guarantees that you're going to make 2 network hops for everything you want to do, right? You're going to go from the user to the app server. The app server is constantly going to be ping-ponging back and forth over to the database tier. That's just nuts if you care about performance. Your in-memory database does not belong on your database servers. Your in-memory databases belong in your application servers, in the application tier. So you can access that data at memory speeds, not at network speeds. And the hook is out. What hardware do you need? You need the hardware big enough to run your database and your apps. You still need fast files. And what's coming in the future? I don't know, more of the same. The bottom line of that slide was, more and more databases are going to be memory centric. New data models will spring up, right? The ones that were cool today aren't going to be cool tomorrow, but SQL is still really going to run the world, so learn SQL. Hardware gets bigger and bigger. The one disruptive thing on the technology on the horizon that might change the world and might fizzle out is non-volatile RAM, right? If RAM suddenly wasn't volatile, right? If you could turn off the machine and the contents of your RAM still stayed around, that really would change the world. But it would also require reinventing the world. Every piece of software ever written, if what's in memory gets corrupted, you just reboot and you reload everything from disk and it's all back. Well, if the copy in memory is the copy, you can't do that. So it really does require brand new algorithms, brand new way of thinking. It really does require us to reinvent 50 years of software development. But if we do that and non-volatile RAM is real, it could really change the world. Will it? I don't know. That was all I had, and we're 1 minute after 8.
You're good.
Okay.
Questions?
Any questions, real quick? Yes, sir.
So, would you be able to talk a little bit about the restart times in the database?
Right.
Because if there are price to pay there,